Hooke's law. Can you write that down? Okay, you got that? Yeah. So look, couple of things to do in Hooke's law, but it's not actually too difficult. So you understand with something like this what happens as you pull on the spring. So you already have an understanding here. As you pull on it, you feel more force, don't you? Yeah. And this actually is Hooke's law. For these types of materials, as you stretch them, you get more force trying to pull it back. Okay? And what Hooke discovered was that the force and the extension has a simple relationship. Hooke's law discovered that the force F needed to extend or compress a spring by a distance x is proportional. That is, F equals minus kx. Now, why is the minus in the formula? It's back, isn't it? Yeah. Yeah. K is constant. It's also called the stiffness. And usually x is a small number.
Of compressing, it won't be minus.
Yeah, it's basically the opposite direction of whatever the x is. Oh, I graded your paper. Better this time. You too.
Was the same test?
Yep.
Was it?
Yep.
Should be better.
Should be, but you'd be surprised with students sometimes. It's not always.
So now do you know when we're getting the report card?
I don't. That's up to whoever your tutor is. Who's your tutor? Neil? Lorraine.
Scariest person.
She is a bit alright. What's the units for K?
N over meter.
Newton per meter.
I didn't know.
No, you're thinking of Newton times meter is joules. Newton over meter is just Newton over meter.
Mm-hmm.
Oh, you have me saying it now. Newton per meter.
Yeah,
Right, you have that? Yeah? Now, just so you know, some books maybe use E instead of X, and some books maybe use delta X. It's just notation. Does anyone know what the natural length of something is?
The natural
force length is 0 on
the normal length.
The normal length, yeah, the first length, yeah. The natural length is like this. It's called L, and the natural length L of a material is the length at which the material tends to return to. It's the length before any force was applied, as you said. That is, it's the length it wants to be at. He's got that? Yeah? Yeah. Continue? Okay. Continue?
Yeah.
The extension. Anyone want to try and give me the definition of extension of a material?
The maximum stretch.
Doesn't have to be the maximum, but it is what you call the stretch. How can we make this a bit more
tension?
Ah, no. You're off track now.
The added length after stretching.
Kind of, yeah.
Distance of like compression and stuff.
Yeah, it's basically the extra length beyond the natural length. It's the length at which the material is extended beyond its natural length. That is, it's the x in the formula of Hooke's law. Okie dokie?
Yeah.
Okie dokie? Okay. Now, we want to have a look at a graph of force against extension. So, there's force, there's the extension, okay? Imagine you have the spring. If you don't extend the spring, how much force is there?
No force.
No force. You extend the string a little bit, what happens to the force? Increases. Like this, right? But what's the slope of this graph? Well, the slope, yeah, it's going to be f over x. But f is kx over k. I'm not so worried about the minus, because the minus is just for direction. So it's just... Thank you. Which equals k. Wow, where have you been, Dammy? Okie dokie. Did you get sorted out? Good. Alright. Were you by yourself or were you with Sylvia? No, you had your own appointment. Yeah, you're going there. Is it just the minors that go together with Sylvia?
Yeah.
Okay. Right, so the slope here is equal to k. But what does the area equal? Does the area mean anything on this graph? Well, let's have a look at the units. What would be the units of the area in this graph? Well, what unit is this in? Meters. And what unit is the vertical in? Newtons. Meters times newtons is the same as Newton times meters. But what unit is that? Joules. So what do you think the area might represent? Yeah, the area is equal to the work done. What work is being done, though? Yeah, the actual work of extension. So we have two results here. The slope of the graph represents the k, and the area represents the work done. Okay, can you copy that down? You all have that already? Yeah? Bello? Wait, are you only starting to write it down?
No,
Okay.
done.
Yeah? Okay. Oh yeah, so actually we could figure out a formula for the work done. So if we look at the graph, what's the formula for the area? A half the base. What's the base?
X.
And the height? But what's the formula for f? Kx. So what's the answer here? So you can actually get this formula. Now you notice how I've changed the name from work to potential energy. Because if you think about it, it is like a potential energy. If you pull the spring, if you pull the spring, it's like you've put energy in the spring. Because when you let go, what happens? Snap. Okay, so it is a stored energy now. Yeah, I think you should write this formula down. The minus, its purpose is only to tell us direction. So for amounts, we don't really care so much about it. Like if I said to you, what is the restoring force or the force or whatever, I don't really care about the minus because it's just to tell us the direction. It's not so much to do with a quantity.
Will they ever ask us the direction?
Yeah, but it'll always be obvious. So like if you extend it to the right, the restoring force is to the left. Do you know? Continue?
Yeah.
Now, in real life, do you know what? Actually, I'll put it. I'll draw it again here. In real life, what you have is this. Usually, we make a graph here of f and x. So it doesn't matter what it is. Something like this. You know, you apply a force, and what happens as you stretch this? The x gets bigger, right? Okay. So the graph will be linear.
Yeah.
But at some point, if you apply enough of a force, yeah, you break it. Or, in the case of a spring, can you imagine a spring? If I pull it out enough, what happens? It becomes a straight piece of metal, and does it snap back anymore? Not really. So, this Hooke's law stops at a certain point, and then it kind of reduces the effect. So this point here, when it stops being linear, this is called the elastic limit. And this part of the graph is called the elastic region. Now, anyone know what this part of the graph is called? Yeah, it's not. It's interesting. It's not inelastic, unelastic, anti-elastic, or aelastic. Any other words? No. Over limit, beyond the limit, end point? No. This part of the graph, breaking point? No, because you need a word that means like region, something region. Deformed region? No. No. So this is called the plastic region. Yeah. They sometimes ask you to draw. No, actually, they like to ask you to draw this in the exam. What you chewing there? Oh, chewing gum.
breaking point.
That's yeah. I know what you're saying. I'm imagining there is a breaking point. That's going to be in another slide. It has a special name. Continue. You have that graph? Yeah. Some terms. Elastic. Now, you don't have to write this down because you have it in the graph. The elastic region is the part that follows Hooke's law, right? The linear part. Plastic, what's that? It doesn't follow Hooke's law, not linear. Elastic limit?
Points where it stops being.
Yeah, point where it stops being elastic and it becomes plastic. Now you don't need to write that down as long as you have it on your graph. Do you have it on your graph?
Yeah.
Yeah, okay. Now, if you were to hang a mass on an elastic material from the ceiling, or if you put it on a spring, it's the same. The mass will obey Hooke's law, obey Hooke's law. And what equation can we find? Now, actually, you know, I used to do the proof, but the proof is long and it's not on the exam, so I won't bother with the proof. But I'll just explain what we have. So imagine, like, you have a spring from the ceiling, and you put a mass at the end of it, and you pull the mass down and you let go. What happens? It'll go like this. Okay, but it doesn't have to be the ceiling. Okay, it could be a spring on the table, and you push it down, and then it bobs up and down. Or it could even be, you know, something coming out of the wall and you pull it back and release and it starts moving like this. Okay? In all cases, it's a spring or something elastic. Okay? There is a formula to calculate the periodic time. Now, this should remind you of another formula. Yeah, but the pendulum, isn't it? So it's kind of like the pendulum formula, except instead of L over G, it's M over K. So what happens to the time if the material has a bigger stiffness constant?
Yeah.
A smaller time. What happens to the time if you hang a bigger mass, a heavier mass? What will happen to the time? It'll be bigger. Okay? Yeah. So this here, very similar to the pendulum formula. I won't do the proof. If you can write that down, please. What's one big difference between this and the pendulum formula? One big difference. What is it?
K.
No, because the K is just like a G in the pendulum formula. Now the big difference is that for these times the mass does matter. But with the pendulum, was there an M in the formula? No, so actually the mass has no effect on the time. But here, is that true? It does have an effect, doesn't it?
Yeah.
Okay, continue. Now, when two elastic materials are combined in series or parallel, then how does the K compare? Okay. I'm going to try and prove this. Sometimes I screw it up though, so just okay. Right. So imagine you have two materials. One material here, which has a constant K1, and then you connect it to another material here, which has a constant K2. Yeah? Okay. And then what you do, you want to know what is the, if you imagine it as one material, what's the new K? And you might think, well, maybe it's just K1 plus K2. Or maybe not. We don't know for certain. All right. Let's see if I remember how to do this. Now, don't write it down in case I screw it up. So you have no, don't write, or you can draw the picture, but don't write anything down yet. We put an F here. So that means the F here has to be the same. And the F here has to be the same. All the F's have to be the same. Okay. So here you have f equals k2 times the extension x2, and here you have f equals k1 x1. Okay, now let's imagine we look at the total picture, and I want to know what's the k here if I combine them. What's the formula for f? Kx. What's the x here? Are you all happy to see that the x here has to be x1 plus x2? Yeah? Okay. Stay calm. Shh. Thinking. Yeah, I'm thinking. I'm nearly there. Thinking. Yeah, thinking. Okay, so k equals f over x1 plus x2. If I just divide, right? That equals f over x1 plus f over x2. But what's f over x1? And what's f over x2? So therefore, k equals k1 plus k2. Right?
How can you divide the denominator?
Oh yeah, you're right, you can't. Oh my goodness. Sorry. Bad teacher. Bad teacher. Yeah, sorry, bad teacher, bad teacher. I should flip both sides. So sorry. 1 over k equals x1 plus x2 over f, which equals x1 over f plus x2 over f. Is that okay? Right. What's x1 over f? x1 over f? 1 over k1 plus 1 over k2. Therefore, the formula is 1 over k equals 1 over k1 plus 1 over k2. Now don't write this down. I said don't write it down. So, if they're in series, yeah, okay, good. 1 over k equals 1 over k1 plus 1 over k2. This is how you combine them if they're in series, using this formula. Okay. Right, well, we look at parallel next. Okay, again, don't write it down. But I think I can do it. With a little help from you, I got this one. So let's try when they're in parallel. So that's when you have two materials like this. And this one is K1, and this one is K2, and you pull at them together with some force F. Okay? Now, here, this F here, and this F, will they be the same? Maybe. Anyways, what I do know will be the same is x1 will equal x2 because they'll move together the same amount. Okay? And remember the formula F equals kx. So what I can do is I can change this into F over k, isn't it? F over k1 equals F over k2. Oh, sorry, I know. Yeah. This F here will be these two added together. Yeah, so you have F equals F1 plus F2, which equals K1 X1 plus K2 X2. But remember we said X1 equals X2, and also it will equal X. Like if I move this 1 centimeter to the right, how much does this one move? 1 centimeter, and yeah, all the extensions are the same. So you get Kx equals K1x plus K2x. So yeah, K equals K1 plus K2. So yeah, if they're in parallel, then the formula is yeah. Success. Okay, so if you can write those two down. It is, isn't it? It is. Except it's opposite. Because, do In circuits, the parallel one is the one over. It's like capacitors.
Remember, it's very similar to the R in the.
That's what Marwan was saying. Yeah, it's similar to this. No. Have you got that? Yeah. I continue? Yeah. So, here's a simple question. A rubber band has a natural length of 10 centimeters and a spring constant of 1. The rubber band is stretched to twice its length. How much force is required to do this? Right, what's the extension here? No, extension is not 20. The extension is 10. What's that in meters? 0.1. So what's the formula for F? 0.1 times 1. So what's the answer here for the force? Yeah, 0.1. So that's an easy one. Don't bother writing that down. Here's a more interesting one. A spring is hanging from a ceiling and a 2 kilogram is put at the end of it and it causes an extension of 5 centimeters. What is the stiffness constant here? So let me just draw the picture here. You have the ceiling. You have a spring here. Then what you do? You hang on it 2 kilograms. And you notice that it causes the spring to extend by 5 centimeters. Yeah. That's all the information. But that's enough information you can tell me what the K is. So if we look at this picture, there's 2 forces here. What are they? Gravity, that's 2G. And here? F, which is, what's the formula? Kx. And what's the X here?
0 and 0.
Now, do you have enough info to get the K? Yeah, what do you do next? Why? Yeah, why? Why? It's in equilibrium. Equilibrium. Yeah, equilibrium is the word. Oh, thank you, Rahman. What is it?
40. No.
No.
Forget the gear. 390.
Okay, you can write that example down. Okie dokie, you got that? Yeah, okay. Let's continue. So, here's another simple one. A spring of constant 2 is attached to a wall and a boy pulls it 10 centimeters. How much work has the boy done? So what formula do we need here? Now half kx squared. What's the k?
10. 0.1.
What's the k?
2.
And the x?
10. 0.1.
Okay, give me the work.
Zero.
10 millijoules. Right. Actually, okay, so I want to do another one, but I think I'll just reuse this one. So back to the example I did a moment ago. This one here. Okay, I'll just rewind it. You have this answer written down? Okay, so the question I'm going to do, you can use this answer to help you. In the exam, what happens is, usually this question has two parts. The first part is to get the k, and the second part I'm going to do with you now. So you have a picture here. Okay, and then in this picture, when we put the 2 kilograms on it, what happens? It extends by, we said, 5 centimeters, wasn't it? Wasn't it? Then what happens is somebody pulls it down an extra 1 centimeter. And what do you think happens when they let go? Yeah, it'll go up and down like this now. Yeah. So the question here is calculate t. Okay, I think you can do this for me. What is it?
1.4.
Seems reasonable. The answer is 2 pi root m over k, which is 2 pi root 2 over, what was it, 392? So what's that?
1 over 7.
As a decimal, please.
0.448.
How did you get yours? What did you do wrong?
2G.
Huh?
2G.
2g? 2 pi?
No, I did 2 times 9.81.
Ah, you used the weight,
Yeah.
not the mass. Okay. What is it? 0 point?
4.487.
So the weight will to the back of the time.
Yep, that's what I said. I guess you weren't listening to me earlier. You. Oh, okay. You're being honest with me. Okay, nice. I like this. Yes, Ming. I said one difference between this and the pendulum. Do you remember pendulum?
Yeah.
Pendulum.
Pendulum.
The mass doesn't matter for the pendulum, but for the spring, does matter.
I mean the distance. Distance.
Ah, the distance. Okay, fair enough. I didn't say anything about the distance. Does the distance matter?
Yes.
No.
No, it doesn't.
No. Did we use this in our calculation?
No.
No. So the distance doesn't matter.
Maybe it's matter of K.
No. Well, this one would matter for K, but not this one. Now, this one is important, though, because what type of motion is this? And the amplitude is the one. The simple harmonic motion, the amplitude is the one. It is.
Is it actually 1?
No, it is.
Or 6.
Not one. It's the distance extended beyond its equilibrium position.
With 5 centimeters
But,
to the weight is at equilibrium.
It's at equilibrium at the 5 centimeter point.
So it's not moving at all, it's just
Yeah.
there.
It's only when I pull it the extra centimeter I get it moving. Yeah? Do you believe me?
So
It doesn't believe me.
the equilibrium with the weight on.
Yeah.
That's 5.
But the weight be a simple harmonic motion in the 5 centimeters.
Correct. It's just sitting there. Yeah. The only way you could get it in simple harmonic motion at the 5 centimeter is if you gave it a little flick to get it moving. Otherwise, it's just sitting there in equilibrium still. You know. Is that okay, guys?
Yeah.
Are you sure? Yeah? Yeah, okay. So try these for a few minutes and then we'll go to the next topic.
May I go to the next?
Go